Hey, good evening, everybody. Check this sound real quick here. Yeah, perfect. All right, so we should have a good sound and everything. Welcome, everybody. Hope everybody's had a great week this week. For my listeners in Florida, hope you guys made it through the storm okay. We did down here. A lot of tornadoes very close to us, but we made it through it anyway. And had some damage nearby towns, but nothing very close to me anyway, 5-6 miles away. But part of living in paradise. So we got the Smurf is in the shop. We're rewiring that hot rod, and I'm gonna have to do some rewiring on the NASCAR. Hey Bill, how you doing? Mike, and how you doing? Not really rewiring on the NASCAR, but I have to make some battery disconnect changes in the car to make it legal for HSR and SCCA. It has to have a driver's kill the button in the driver's area within reach. Hey Chris, how you doing? So got me thinking, since I'm rewiring Smurf and I got to do my car too, I think it would be a good time we should talk about battery kills and relocations and all those things. Some other stuff that is going through the shop right now. We did get the radiator in for Mike's car. Hey Ryan, how you doing? So I can get that thing in. The shipping isn't completely up to speed yet. With the hurricane and stuff, I don't know why in our area it's delaying, but we're getting caught up. But that's pretty much it for this week. Been working on the Smurf, trying to get that thing ready to go testing. Had to do a little bit of stuff on the Chevelle, but pretty much had to put that on hold to go ahead and get Smurf done. So on that car, I wanted to clean up the wiring. The wiring was done probably 4 or 5 years ago, and it seemed like they used a complete stock Holley car harness, which you guys have seen on the channel. I usually, even on a regular passenger car, I cut those up because they're extremely long and a lot of unneeded things in them. And he also had a bunch of bus bar type strips on the car, so it was just a lot of unneeded double wiring. And when you're racing and you're trying to make your car as light as possible, well, you look at every possible thing you can do. So when I pulled all the wiring out of the car, the box weighed about 38 pounds. That was with the ECU and a power grid. And some of that has to go back in the car. So I will know next week what the difference was in the wiring from what we took out and what we put back in. So interesting to see how that works out. Kind of the things you gotta look at when you're looking at that. So you're gonna do a battery relocation kit in your car. A lot of times we want to get the battery out of the engine bay in our hot rods just because it doesn't look good. You can put covers over it and stuff, but you never can get that clean look with the battery in the car under the hood. So relocating it to the trunk or was always the big go-to thing, especially in race cars. And then they would go, because the starters weren't that great back in the day, they'd go to 2 batteries and stuff like that. And nowadays we're putting the cars, because now we can run lithium and AGM batteries, which do not vent, so we can put them in the cockpit with the driver. Move the weight. We can move that weight wherever we want in the car. So it just makes sense to talk about that You guys might not know all the ins and outs that we do in racing, and but it'll all apply to your guys' cars as well. So why don't we just go ahead and just get into it right now. I don't see too much need to wait around too much more. So let me switch screens here. Switch screens to the right screen. So this is the typical starter battery wiring on the left-hand side that you would see, in a passenger car. So you got your battery, it goes through the battery post on the starter. You got a S wire, which is solenoid for start, and that goes, through your ignition switch and your neutral safety switch. On an old school car, you would have the R, which would power the ignition coil on a points car. So you're going to still do the same thing when you wire it, when you put the batteries in the trunk. A lot of times we would use a remote solenoid, which helps in the starter output, because now the solenoid on the starter gets hit with more amperage and more voltage, because it's got coming directly from the battery. Whereas in the original system, you got your wires coming off the battery post through a fusible link, through the firewall, through a fuse box, through all these connections to the ignition switch, then down to the neutral safety, and then finally returns to the solenoid on the starter. Well, what happens a lot of times is you get voltage drops. So even though the starter has 12 volts going to it on the battery post, the S wire, the solenoid wire, sometimes can be as low as 8 or 9 volts. There's a lot of, like I said, a lot of voltage drops. And then that's when you have starting issues. We ran into that with Scott's Corvette here recently. So when you do a remote solenoid, now you put a jumper between the battery post and the S terminal on the starter motor itself, and then you hook your ignition to the S on the remote mounted solenoid, which is usually a lot closer to your ignition switch, so you're eliminating wiring, and you can run heavier leads to that. So it just helps in the voltage drop. Besides the fact that the solenoid on the starter is in the engine bay next to the headers, it's getting hot, so it requires more voltage. And the remote mount solenoid you can mount inside the car, and it won't require as much. Chris says, in a lot of cars with kill switches in the back of the car, is that required? It depends on the sanctioning bodies. Usually, like SCCA and NHRA, IHRA, they want a switch mounted on the car. In road racing, they want a lightning bolt next to this switch, because they don't necessarily denote where you have to put it. So they want that so safety crews can see it. On drag racing, they always want it on the back of the car. That way, and also on drag racing, they want it push to off. And the reason is, driver crashes the car, knocked unconscious, whatever the case may be, a safety worker approaches the car, they want to be able to kill the switch and shut everything down in the car. If the engine has stalled, you could have fuel pumps running, you've got all these components in the car that are energized with power, and you may have gasoline or other chemicals spilling, and so they just want to kill all the voltage in the car so that they can eliminate fires. So that's the reason why they do that, and you just have to check the sanctioning bodies that you race it with, what they do. Usually, like in autocross, they don't really have anything with that. I'm not familiar with what Champ Car does with that. I know Chris runs Champ, but I know HSR does require it, and HSR kind of goes by SCCA's rules, kind of a little bit more liberal. Very similar with NHRA and IHRA. NHRA kind of makes the rules, and IHRA just kind of copies it. They may not totally enforce everything that the NHRA does, but they follow suit. So that's what you'd want to do. You know, obviously your battery probably would relocate to the back of the car. This is a type of battery switch that's you twist it. Very common in drag racing and in all auto racing. Typically, these switches are 2-post. So I don't think SCCA has the rule, but NHRA and IHRA do have the rule that when you shut the battery kill switch off, that it shuts the car off. Now, if you're running an alternator and your alternator is going to the positive side of this, to the car side of the switch, the car will not shut off when you break the switch because the alternator is putting out voltage, so it keeps the car running. So that's always been a problem, especially when we're doing street strip cars, and you know you have the alternator, and every now and then the tech guys will walk around the back of the car and hit the switch during tech, and the car has to shut off. If it doesn't shut off, they won't let you race. So there's a number of different things you can do to fix that. But before we get in that, let me just show. I got my slides a little messed up here. What I wanted to show in these next couple pictures is if you're mounting 2 batteries in the vehicle. So with 2 batteries, there's series and parallel. If you connect them in series, you have the power going to the switch or to the car, and then you use the negative to the positive on the next battery, and then that negative would go be the negative side. That doubles the voltage. So every time you add a battery, you're adding voltage. So 2 12-volt batteries would make 24 volts. We don't want that. So you want to run parallel. So in parallel, you hook the power to power, ground to ground. But there's an issue with that. If you hook your batteries up in this schematic here, even though they're calling it a trolling motor, you do get excuse me, you do get more cranking amperage. Sorry, but your charging system, whether it be your alternator or if you're charging the battery between rounds or between races or just for storage, it's going to read this first battery. So the second battery, when they're wired like this, will not charge. It may, but a lot of times you'll find this battery will be fully charged. This battery will be about 50%. So whenever you wire them, even though we're running parallel, you want to excuse me, you want to connect to the car in a different manner. This is what I would consider the correct way of doing it. So you got 2 12-volt batteries. We're connected in parallel, so we still only have 12 volts. But we're bringing the power side off of one of the batteries and the negative side off of the other battery. So now, when you hook a alternator up or a charger up, the unit will sense the voltage of both batteries because you've hooked them up in this parallel system. So it's reading the power off of one side, the negative off that side. So 99% of the time, both batteries will have the same exact charge when it's connected this way. Now, the one issue there is if one battery is starting to go bad, then it creates other problems. But I just wanted to show you this because a lot of times I would get race cars in the shop and one battery would be stone dead. They have starting issues. Like, I got 2 batteries in the car. They're only 6 months old, blah, blah, blah. And then you go and you disconnect the batteries and you check them independently. And you find one fully charged, one dead. And the problem is when one is dead, now it's drawing off the good battery. So you don't even have all the amperage of your good battery. So this is if you're going to use 2 batteries. Not many people wire cars with 2 batteries anymore. But if you were, this is the correct method to do it. So now let's go back to the battery switches. So Your typical battery switch that you see advertised is going to be a 2-pole like this. So you can either do this on the ground leg or the power leg, it doesn't matter. But if you're running an alternator, that throws a monkey wrench in there, because if you kill the negative side, the alternator power is still going to the battery lug or to the same wiring in the car, and it's picking up ground off the car's picking up ground off of the frame or whatever. The car will stay running. It's not going to shut off. It won't pass the NHRA emergency test. And just to let you guys know, do not use these type battery switches. This one has a little key and it goes down and pushes a plate against the contacts. It's fine for something that's low amperage, but it won't work when you're trying to get 500 amps to your starter to crank your high compression engine over. So I do not like using these. I've always found many issues running them. So just that's my take on it. Some people use them and they may be fine, but I don't like them, and I see a lot of issues with them. But getting back to our alternator system, this is, if you're running this style switch, this is the only way you can make the car shut off without having a onboard relay system. So on a unit like this, you connect one power, your battery to one post, your positive cable to the front of the car on the other post. You make a loop to one of the little posts with like an 8 gauge, and then the other one would be directly to your alternator. So when you wire it this way, when you kill the switch, it kills all the power in the car, including the alternator. When you do it with the other systems, if you let me step back a second. So if you're going to run your alternator directly to your battery and use the battery switch to cut all the power to the car, that will work and it will pass the NHRA test. However, the alternator wire still has full battery voltage going to it, and that can create a problem. I've worked on cars like that. You kill the switch, you think the car is dead, you go to start pulling the motor out of the car, and you got a live 6 gauge wire with all the volts and amperage coming out of the batteries. It's live. I mean, you can create a fire, you can arc stuff together. If the car has electronics, you probably fry the electronics by throwing a voltage spike through the car. It's just not good. But back in the day, we were fighting with this 10, 15 years ago, trying to figure out how to get the car to shut off and pass the NHRA test and still have an alternator, especially when it's a street car. But this switch will fix that problem, because now you're dual contact. So you're killing the battery wire and you're killing the alternator charge wire. So when you do that, everything's dead. You're good to go, and that's the best way of doing that. And these work good too. Even if you're not going to race your car, but you're going to put your battery relocated to the trunk or to somewhere else in the car. These switches work really good as a anti-theft switch too, because now when you flip the switch, the car is dead. So it wouldn't be good if you had an alarm system, but the thing is, the car is dead. The car would have to be towed. They can't start it. They can't jump, hot wire it, whatever. They can't move the car unless they're going to tow it. So it is one form of anti-theft you could do. I've done it before with one car where we wired the alarm system directly to the battery, because the alarm isn't going to take any amperage. It's not going to stop anything as far as legalities for any sanctioning bodies, but yet the alarm was still connected, but everything in the car was dead. So if somebody broke into it, the alarm would still go off, but yet again the car would not be able to move. My buddy Doug had a problem back in the day. Somebody stole his Mustang, and it had it parked right next to his bedroom window, but somehow they were able to had multiple people, but they popped the hood and cut the wire to the alarm quick enough that nobody noticed the alarm going off, and then hot wired the car and drove it away. So in a situation like this, that would have stopped it because the car would have been dead, and they would have then had to figure out, where it was or whatever, how to get the car turned back on and stuff. So just little tidbits of information there. But like I said, so here's some other systems that we used back in the day. So you could put the switch, a lot of times the switch would be mounted on this, too far back. These switches would be mounted on the bumper or in the taillight. If you wanted to make it a little cleaner, you would use a system like this where it would mount inside the trunk, and then you got a pull handle that would stick out the back of the car. Whenever you do relocate the battery, you want to make it easy to charge, especially when you have a race car. We use these charging lugs you saw on Dave's car. I put these lugs in. They're tucked in behind the bumper. You won't see them unless you're looking under the car. But with his battery in the trunk, now he doesn't have to worry about taking all the interior panels out, because the trunk area will be fully upholstered, so you can't see the battery box or anything. So with these charging lugs, you can keep the batteries maintained. If the batteries go low and you have a problem starting it, very easy to jump start the car. So it works out real well. So just something to think about if you are relocating your battery. You want to be able to make quick access to keep the battery charged. This is a good way of doing it. You can get these different lugs. These actually have a nice little dressing on them, and these you just drill a hole and you put them in whatever kind of panel you want. These are typically all copper, or brass. So I mean, they'll take 800-900 amps to go through them, no problem at all. So it works real well. Just a little bit of information when you're working on your car. You can or laying it out, you can figure that out. And of course, whenever you go battery, if you're running the battery through the car, like we typically will, we don't want the battery cables hanging under the car. We use these bulkhead connectors to send the power back into the engine bay. It makes it nice and clean. You can tuck this up under the carpet or in another convenient spot, and it just makes it easy. You don't want to try not to run your battery cables through any metal surfaces, because if it's sharp or anything, it can cut the cable, and then you've got a dead short. With a large battery cable, it's going to burn. It's not going to be pretty. You can do it with grommets, but you really got to make sure your grommet is very well seated, because sometimes with the cable going through and it's bent at an angle, you can over time work the grommet out of the position, or the grommet could over years could decay and fall apart, and then you have to worry about your battery cable cut. So if you use a bulkhead connector like this, the battery cable is bolted to solid on either side, can't make contact with the body. You don't have to worry about anything like that. It's just a very foolproof way of doing that, and makes it a really clean installation. So a couple 8-10 years ago, we started seeing the AGM batteries, and in the last couple years we started seeing a lot of the lithium batteries coming into play. And with like radial cars and stuff like that, a lot of cars we try to get the weight out of the back of the car. So the new norm is to mount the battery in the cockpit on a race car. And like on the NASCAR Cup car, the battery is mounted in a box behind in front of the rear wheel, so there's no access to it. So a lot of people started doing this. They would make a Morris cable go up to the car. A lot of times they'd even do it to guys would put them on their shifter. And that way, if you got in the car and you're all strapped in, you forgot to turn the battery switch on, you could just reach over, pull the lever. The Morris cable would then turn the switch on, whether it was mounted in the back of the car or wherever. And so same thing when they started mounting the batteries inside the car. NHRA requires the switch to be on the back of the car, so you'd have to run a Morse cable all the way to the back of the car, so you would have your push-pull switch, or you would have to put your battery switch all the way in the back of the car and run battery cables from the front to the back and back to the front and then to the engine, which just didn't make any sense. So we started using systems like this. But there's a better system out now, and this is basically how we do them now. We use a system like this where we have a continuous duty contactor, and we use a emergency e-stop switch in the back of the car. So now the only thing that has to go from the battery or from the switch here is just two little 14 gauge or 12 gauge, depending on which unit you use. This one needs a little bit more amperage, but there's newer ones now that have a circuitry built in, so it's very low amperage to operate the contactor. So a lot of cars that I wire up, we only run 18 gauge wires. So two 18 gauge wires to the back of the car instead of having 20 feet of 1/0 battery cable. So obviously you can see right away there's a huge weight savings. And this is what I'm going to do on the Cup car. Rather than running a battery switch on the dash and having to deal with the alternator situation and everything else, I'm going to put an e-stop switch on the dash and run this inside the car with all the stuff going to it. As you can see here, you got your one lug is going to be battery connected to the battery, so that's going to be full time. And then this side would go to your car. And then this is kind of misleading the way this is wired. It's not right. This wire should be going to the switch, and then the switch would go back to this. Or, well, actually, I guess if they used maybe they're using the negative side for the switch. So in that case, you'd only have to run one 18 gauge wire to the back of the car, and you could ground at the back of the car. But so it's a very simpler system. Doesn't require a whole lot of weight to be added to the car, and there's a bunch of different kind of contactors that you can use. This is another one. Most of these are very, very solid state. They can take quite a bit of amperage. This style and the style previously, I think, can take 300-400 amps. But there's some that you can even put more to. But it's the same thing. You get your battery on one side, vehicle on the other side. You got a power and a ground here that makes the contactor go from no contact to full contact. And you do that so it's very little amperage draw. This is one of the more common style that are used in drag racing now. And as you can see in the writing on it, 250 amp continuous, 900 amp surge. And this on the back side of it, I don't have a picture of that, but it's got a amperage limiting circuit on it. So this thing takes like 5 millivolts to operate, almost no amperage at all. So it can be in the car left on forever, and it wouldn't even run the battery dead or anything. So very good system to do it. Here's another one. This is another high amperage one, but this one will take a little bit more amps to control. But still very good way of doing it. And this is the typical switch that I use. It's made by Honeywell. It's an emergency e-stop switch for machinery. So you pull to turn the car on, and you push to turn the car off. And it's already wired with a Deutsch connector, and it's all covered up on this side. So my thought was the other ones, the back of the wiring is all exposed. So if the car had backed into the wall, I guess it could be a possibility that it would stay connected even though somebody's trying to shut it off. So this one's is completely sealed off, and it looks a little nicer. So this is what I usually typically we'll use. And there's the switch on the Smurf, and just simple pull on, shut, push for off. So it makes it legal for racing. You hit that switch, the car will shut off. So it makes it all good, and it's all lightweight. And on his car, we're running a Braille lithium battery. I think the battery is like 4 pounds. And you can see we have our charging lugs. So I use these disconnect lugs. I put that on the battery charger. So you just go in there and clip the battery charger on. You don't have to worry about getting the alligator clips on the right post on the battery. It just plugs in. You can't mess up. Works very good. And there's the contactor, and the contactor's been in the car for a while, so it's not the cleanest component, but it works. And there you can see this has got the current limiting feature on it, so the wires going in there are on there, and then the power and ground to actually function are there. I've never seen one of these apart. It probably has like a capacitor or something like that charges up, so it doesn't take any power to control. And then we have our main vehicle fuse for the car. So this black cable with the red end, that goes to the starter. That gets straight battery voltage. And then this is 150 amp, and that goes to everything else in the car. So even though all those components may not be fused individually, we still have one major fuse that will disconnect in case of a major catastrophe. So that's kind of what how you have to, how you need to do it, or how you should do it if you're going to relocate your batteries. You don't have to. You can just hook up a battery in the trunk and run the wires. If you're not racing it, it's not. There's no rules on how you want to do it, but for longevity and for proper use of the car, in safety wise and stuff, it's always good to put some type of battery kill switch so you can disconnect the car from power when you want to work on it. It's very easy to not think about disconnecting the battery, but it's a little easier to remember, just go out and flip that switch and kill the car. Like I said, it's a good anti-theft system. So it just works well. And it's just how we should do it, I guess. I wanted to show, let me look for this picture here. I wanted to show you, I'm sure you guys might remember, this is the thumbnail that I had for the channel. And this is on Kelly's car that I wired up recently, and it's basically the same thing. We got the Braille battery. We got the same, because I do them all the same. So battery charger connector right there, so you can plug in. Very easy to do. And the nice thing is, when you have a team of multiple cars, we have multiple battery chargers. They all, even the spare battery chargers, all have that connector on. So it's very easy to just plug in and make it work. And then there's our contactor switch, and you can see that on the outside of the contactor switch, the side it switches, there's our battery cable going to the starter, and there's our cable going to our interior fuse, just like on a Smurf. Same, they all get wired up exactly the same. It helps with when you have multiple cars with the same stuff, because now the components will all interchange. You're at a race and one car is down or whatever, and a main fuse blows, you don't have a fuse, well, you can pull it out of the other car and make it work. I try to do that when I'm doing any wiring on anything like this. A big thing with the rewire on Smurf was a lot of the specialty components, dry shaft speed sensors, a couple of the other data uh, uh, data sensors, like your G meter and stuff like that. They had specialty connectors on them, which was nice. I mean, good to have some kind of connector on them. But the problem is, if you say the wire rips out of the dry shaft sensor, or it just starts reading erratically. If you have a specialty connector on your sensors, you can't go and ask somebody to borrow theirs, because it's not going to work on your car unless you have all your wiring stuff with you to make all the connections the same as you did. And a lot of those specialty connectors take specialty tools. You're not going to bring a whole slew of connectors and terminals and different crimpers, for the just in case. So when I started doing the rewire on Smurf, that was the first thing I did. Was anything that didn't have the sensor connector that would come from the manufacturer, I switched them out. It just makes it so easy. You got shock sensors and dry shaft sensors that if you use the race pack sensors, a lot of the aftermarket ones they all followed suit with race pack, because they wanted to be able to sell their components to race pack users. So now that the car has got all those connectors back on, now if we ever have a sensor go bad, we can go to to somebody that carries racing stuff and buy one, or a vendor or something like that, or we can go to a competitor or somebody else that's at the track and borrow one, and it will go plug right into our car. There's no rewiring. It just makes it so much easier to do it that way. So that's just one of those things that when you're wiring up stuff, you want to kind of think about stuff like that. So I unfortunately was not able to get the EFI harness finished today for Smurf, but I wanted to show you some pictures on this stuff that we can go over, kind of show you how I do. I mean, you guys have seen before. I use my vacuum hose method for measuring and stuff like that. So I threw one more part at this one. So let me go over this and show you guys this, since tonight's about wiring. So there obviously is my tape measure, my vacuum hose, and there's my list. Go over. You can see on the list I got ECU to the grommet and the firewall, and then grommet to the first trunk. And what I denote as a trunk is where the wires are going to branch off the main harness. So that's where the first branch is, 10 inches past the grommet. And then I got the first trunk to the injector, 1 inch. First trunk to intake air temp and map, 18, 19 inches. And then that's the only thing that's really in the back side of the engine bay. All the other sensors are going to be in the front. So then we go grommet to front, to first trunk, then to second trunk, which is going to be somewhere at the beginning, at the front of the engine, probably in the middle of the intake. That's on this particular vehicle exactly how it is. So that's 29 inches. And then from the second trunk to TPS, 44. Fuel pressure sensor, 45. Oil pressure, 46. Coolant, cam sensor, crank sensor. So you kind of get the idea. I'm building a roadmap. And then the coil wiring is in the back of the engine bay, and it doesn't go to the engine. It goes to the frame, to the coils. So we have grommet to even coils, grommet to right O2, which is both on the passenger side of the vehicle, and then grommet to first trunk to third trunk. We're not going to go straight to the front of the engine for the second trunk, so we're going to bypass that and go to a third trunk, and then that's where you're going to get your odd coil and your left O2. So that's how I do that, figure out all my measurements. That way now I know how long the leads need to be. Oh, I had a close-up. So there's that again. So what I did different this time, because normally I just do it on a bench and I got stuff holding the wires down, or I got cable ties where the trunks are going to go, and it just you end up cutting the cable ties 25 times as you're adding wires and stuff. So this time I decided to do it on a board so I can lay it out like it'd be in the car. So this trunk here, that's the first gate. That's going to be the grommet in the firewall. So everything from here back is inside the car. From there out is in front of the car. So, and then over here is our first trunk. And you can see I got it on the next slide, I think. Yeah, so there you can see where here's the third trunk in the front. No, I'm sorry, the back. So this is the first trunk, center of the back of the engine, where the injector harness is. The map sensor is on the back of the manifold, so that goes right there. And then we're going to come out of here, and we're going to go over here to a third trunk, and that's going to be our coils and left wideband for against the back of the firewall. This is on the opposite. This is our grommet position. This IAT goes to that first trunk, and this is the right side of the firewall where our even coils and right O2 sensor is. And then we go forward. This would be at the front of the engine, and we have cam sensor, which is right on top of the engine. We have our oil, fuel, which is on the driver's side of the engine bay, crank, which is obviously at the bottom of the engine, and then coolant and TPS. Coolant is near the radiator, and the TPS is up on top of the intake manifold. So those are just laid out so that we know how far everything needs to go. There's just another close-up of those. So here's how we start our wiring. So I get a harness kit from Holley. It's an unterminated kit, so it gives you 10 feet of wire for every terminal in the J1A, which is inputs, and J1B is outputs. And it gives you the left side O2 harness, and it gives you two shielded cam crank harnesses, whether you can use a distributor or crank and cam sensor or whatever you would need. You still need those to make the vehicle operate. So I lay that whole thing out, and then I start looming it into the position. So I take my sheets here, and I don't know if I can show you guys. So you can kind of see on this part, depending on what how you're looking at this, I've got little lines back here, and those are things that are in the harness that I don't need for this project. So I can get rid of those wires out of the harness, make the harness smaller, make the harness lighter. So now I can start putting the harness through its stages, and being that this gate is laying that way, you can see how the wires are kind of making an S through it. Well, that's how it's going to be in the car. The firewall is parallel to the front to back, so the wire has to make that S turn to get through that grommet. So that's what I try to simulate it so that everything's going to lay out as it would as if it was in the car. So at this point, I've got coils for the left side. I've got the wideband for the left side, and you see there's gate 3. Here's gate 1. That screw there is the injector harness, so you don't see it because that's actually the whole injector harness at this point. It gets cut off. And I've got my signal return for the map sensor, signal return for the intake air temp, signal return for fuel, oil, coolant, TPS, and then those are our ignition wires for the cam and crank. Now, these harnesses aren't going to have all your splices and everything built into it, so you have to do all that stuff into it. So that's why you want to keep your wiring schematic close at hand, because you have to build all this out as you go. Here I've got the right side coils harness in, and even though this ECU I'm just using as a fixture, it doesn't have the J2A, which is input for the right hand O2 sensor, but I laid it there and I've got the bolt there where it's going to, that's like a positioning that everything has to go up to and go around that corner to get to go farther along. And what I did, just to let you guys know, all these screws I put rubber hose over them so that there's no chances of chafing a wire, dragging them in and out of there. So here, now you can see my map sensor. I got an orange and a black. That's 5-volt ref, ground, and I got my red with a black tracer, which is my signal return. Same with my fuel and oil, coolant, and TPS. So I've made my splices and brought my 5 volts out to where they needed to go. I made my splices on my grounds, and my grounds go out because your coolant and your intake air temp take a ground. So the computer sees a resistance from ground, and that's how a thermistor circuit works to show temperature. So I didn't get any of the other, I didn't get a slide, but now you can see that there's 3 relays here. So you have to have a power relay for the power up your injectors, because your injectors fire on the ground side. The ECU sends a ground signal to the injector, and when it gets power and ground, it fires the injector. And then, being that this car runs the IGN big smart coils, we have to have a power circuit and a ground circuit for each coil. So instead of running a 70 amp, which wasn't, I wanted to keep them all matching, so these are all 40 amp circuits. So I got one for the left bank, one for the right bank, one for the fuel injectors. Now on if you're running regular Holley smart coils or LS smart coils and regular injectors on a street car or even a race car that's, maybe not super high power, you can get away with one relay to do all that. But being we're running, large dwell cycles on the coils to get a really hot spark to fire all that nitrous, to fire all of the nitrous, not a lot of nitrous, all of the nitrous, you need more amperage. So Holley says in their big wire smart coil kit that they want you to run 70 amps to each, to the entire coil pack, or divide it into 2 40s. So that's what we did on this. That way we got everything all looks the same. Now, all this wiring comes off to the side. This all is going to connect to the car. These are inputs and outputs that are going to go to different circuits, and then we got our powers and grounds that are going to go to our battery lugs. But you can see now I've got the harnesses all laid out. You can see here's one trunk. That's trunk 1. Here's trunk 2. There's trunk 3. Wait, I'm sorry. This is the grommet. This is trunk 1, trunk 3, and trunk 2 is out here. So, unfortunately, I wanted to get all the connectors on, but I just ran out of time. But that's so all these connectors. Being this is going to be on a race car, you're pulling the engine out all the time. There's a lot more fluids and stuff getting on the harnesses and stuff. Even though I still use my F6 loom, all the joints are heat shrinked. So you don't have to worry about electrical tape getting oil under it and coming apart and making the harness look aged as it goes. And then on every leg, you can kind of see here, there's heat shrink there. So now I'm going to make the connection, and then I'll slide the heat shrink up and heat shrink the opposite end, which then will go right to the connector. So all the wiring will be nice and neat looking. The other thing I'm going to do, and probably one of the main reasons why I didn't get all the connectors on it, I'm going to take heat shrink, white heat shrink with my printing tool, and I'll print labels for all the connectors. I know where they all go, but somebody else might be helping me work on the car. They may not know where it all goes. I just think it's just nice and clean. it makes sense to have the everything terminated and have everything labeled what it is and what it does. That way, when you're pulling the motor out of the car and you're putting it back in the car, it just all makes sense. If you we don't have that issue with this car, but your own personal hot rod or something, you may mess up the engine, and it may be apart for 6 months or a year. So instead of having to pull the harnesses back from the connectors to try to figure out what color the wires are, so you can go through your diagrams to figure out where they go, they'll have a printed heat shrink, white heat shrink on each wire, so it'll tell you where it goes. So it just makes it a lot easier. To me, it makes a lot of sense. So that's how I do that. So again, there's the battery shut-off switch, e-stop, and these are pictures I used in the other slide. So same things.